So our next spectrum that we're going to look at is for bromobenzene, which has the chemical formula C6H5Br. And if you go to your periodic table and look up the masses for each of these elements, 12 for carbon, 1 for each hydrogen, and 79.9, which we'll just round to 80 for bromine. You'll expect that we would get a parent peak of 157. So let's look at the spectrum. Now what you may notice, and should notice, as you look carefully on those peaks, is we have a prominent peak here at 156 and a prominent peak at 158. So one higher and one lower. But the peak at 157 is really, really small. So how is it that we have a peak that's higher and a peak that's lower, and the peak that we're expecting to see itself is actually very small? Well, it gets into something that we've already talked about with another element. We talked about this with carbon, but we're seeing it in a different way now. And that's to again look at the isotope patterns for bromine. So for bromine, we have two naturally occurring isotopes, bromine 79 and bromine 81. And they're present in almost equal abundances. What about bromine 80? Well, it turns out bromine 80 is not a stable isotope. That mass that we used on the periodic table of 79.901 is based on the fact that we have a 50.7% abundance of bromine 79 and a 49% abundance of bromine 81. It turns out the half-life of bromine 80 is only about 18 minutes. It's not a stable isotope. So if we now look at the two possible bromobenzene molecules we have, C6H5 bromine 79 and C6H5 bromine 81, we can add up their masses and we find that we get 156 for the bromine 79 and 158 for the bromine 81. And those are the two peaks we saw. So halogens are often one of the tougher groups to find in spectroscopy because most of the common techniques that we use aren't going to point out a halogen to us. There's just no way for that halogen to appear. So mass spec, it turns out, is probably the easiest way to see a halogen. So for bromine, if we have bromine in a molecule, we will see an M plus and an M plus 2 peak. And in addition to that, the ratio of those peaks is that the M plus 2 peak is about 98% of the M plus peak. So again, we can see bromine by finding these two peaks and seeing that they're at a 98% ratio. Now, if the ratio is closer to about 1/3, then that's usually a strong indication that we have a chlorine. We can see that here. Here we have an M plus that's at 100 and an M plus 2 that's approximately a third the intensity of the M plus peak. So that tells us that this molecule contains a chlorine. Why the 1/3 ratio for chlorine? Well, the mass we find for chlorine on the periodic table is 35.453. Just like bromine and carbon, and like pretty much every other element, we have more than one stable isotope for chlorine. In the case of chlorine, it's chlorine 35 and chlorine 37, and chlorine 35 is about 3 times more abundant than chlorine 37, and so that's why we get the pattern that we do here. So again, just to summarize this, if there's an M plus and an M plus 2, if the ratio is very, very close to 1:1, then that means our molecule most likely has a bromine. But if that ratio is more like 3:1, then that's an indication we have a chlorine within our molecule. All right, one final rule that we want to be aware of, which is known as the nitrogen rule. The nitrogen rule sometimes allows us to detect nitrogen within a compound that we have a mass spec. So if our M plus is odd, then that tells us we have an odd number of nitrogen. But if M plus is even, then we have an even number of nitrogen, which can, of course, include having 0 nitrogens. So our next spectrum will help us to see that. And so this here is our parent peak at 93. The peak that's one higher, 94, is our M plus 1 for a molecule containing a C13 in it. Now, can we determine a chemical formula from a spectrum like this? Well, yes and no. Solely from a mass spec, we can make some guesses, and we can come up with some pretty good guesses. But that's all they're going to be from a mass spec is guesses. Because there's a lot of functional groups that we can't really discern from mass spec. Ethers don't really show up very well. Alcohols we can certainly see, but they're going to be missing 18 most of the time. And so we've got to go to the IR to determine that. Carbonyls, a lot of carbonyls fragment very easily right next to where the carbonyl is. So we can make some guesses based on mass spec. And we're going to do some of that. I'm going to do an example here in a moment. But the reality is that we really need other spectra to go with mass spec to determine what's going on. But what could we do with this one? Well, we know the parent peak is 93. Given that that's odd, we know it has an odd number of nitrogens. So here's the first guess we're already going to take. 1 nitrogen, 3, 5. We know it can't be more than that because if we had 7 nitrogens, that would total to 98. but we know it has 1, 3, or 5 nitrogens. I'm going to pick 1 nitrogen because on a molecule this small, that's the most likely candidate. But who knows? So as I said, we're taking a guess. And so with problems like this that you might run into either in the practice problems you're going to do next, or on a quiz or an exam, when the question asks you to come up with a chemical formula just based on a mass spec, it may not be the exact chemical formula, but we're just looking for a chemical formula that's reasonable given the information that we have. So I'm going to start with our 93 here and subtract out 14 to get to 79, because that's what's left after we subtract out 1 nitrogen. And then I'm going to make the assumption that everything else that's left in this molecule is carbon and hydrogen. So how many carbons are we looking at? Well, if we look at C7, that would mean we'd have mass of 84 from carbon. And 84 is clearly greater than 79. So we can rule that out. It requires too much mass. We could go down to 6 carbons. That equals 72, which would leave us with 7 more hydrogens. That could be okay. And if we go down to 5 carbons, which is 60, then we would need 19 hydrogens. And it turns out, given the number of carbons in your molecule, there is a maximum number of hydrogens, and this has exceeded it. So under the assumptions I made here that 1 nitrogen was more likely than 3 or 5, and also that the rest of the molecule was carbon and hydrogen, we've come up with the only possible chemical formula being C6H7N. Now, if we also had an infrared spectrum or an NMR of this compound, we would know more about the functional groups that were present, and we could be a little bit more certain or make modifications to this chemical formula. But if we're just working from the mass spec, this is as far as we're able to go.